Davis for their help setting this up, and the Center for Public Impact, the director V. Rosser, and Esty Miller, who you probably received an email or two from in the past week. Esty does a lot of work for us, as well as Laura Mosler. And WBGSU, especially Tom Cummings for the work that he's doing to help us put this on tonight, and Peter Fairburn from our marketing communications, who put together all of the great materials we've been able to distribute to get all of you here tonight. So with that, no one's here to listen to me speak, and that is perfectly fine. My name is Timothy Davis. I'm the director for the Center of Great Lakes and Watershed Studies, and that's all I'm going to say about me. But I'm really excited to introduce Dr. Angelica Vasquez-Ortega. Dr. Vasquez-Ortega joined BGSU at the same time I did in 2017. Dr. Vasquez-Ortega comes to us from the University of Arizona, where she received both her master's degree and her PhD. But before that, she received her bachelor's degree from the University of Puerto Rico. Dr. Vasquez-Ortega focuses her research mainly on nutrient dynamics in agricultural soils, and focusing on different best management practices as it comes to reducing the loss of nitrogen and phosphorus into the western basin of Lake Erie and other nearshore regions of the Great Lakes that cause things like harmful algal blooms and hypoxia. She's also interested in studying the benefits associated with amending agricultural soils with dredge materials, which are materials that are taken out of the lake to maintain shipping channels. And lastly, she's interested in studying the role of dissolved organic matter, which Dr. Vasquez-Ortega will go into in a little bit, in phosphorus sorption into iron oxide filters. So those are some big terms, and Angelica is going to break those down for us tonight. But I'm really pleased to introduce her. She does some really interesting work and is a really important component to the Center for Great Lakes and Watershed Studies. So thank you, Angelica, for being willing to speak to us tonight, and take it away.
Okay, awesome. Thank you. So again, my name is Angelica Vasquez-Ortega, and today I'm going to be telling you a little bit about what I do at BGSU. So the title of today's presentation is how Ohioan agencies, as well as higher education institutions and farmers in the area, how we're working together to clean our regional waterways. Before going into more details related to the presentation per se, I want to thank the collaborators, because without them, I couldn't be able to do any of the research that I'm going to be presenting you today. So I want to say a special thanks to Dr. Margaret Kalsick at The Ohio State University, Dr. Chad Penn at the USDA in Lafayette, and Dr. David King at Ohio State University as well. Most of the funds that were used in order to conduct this research came from Ohio Sea Grant, as well as all the other logos that we see here, the Ohio EPA, the Great Lakes Restoration, and so on. So I want to acknowledge and thank the funding agencies that supported this work. Well, let's start a little bit broad, no? And I will take you down to the specifics. So I want to start with this simple, maybe not so simple, maybe a little bit complex diagram in which I am showing different land uses, and these are proxy, very similar land uses that we have here in Ohio. So we have urban areas, agricultural areas, residential areas. And the point that I want to bring with this diagram is that all of these land uses are contributing to some sort of pollutant that are going to be transported, in this case, via water transportation, and they are going to be reaching rivers and lakes. In our case, they might be reaching the Maumee River or our Western Lake Erie Basin. And if we think about one of the pollutants to be nutrients such as phosphorus or nitrogen, or phosphate and nitrite to be more specific. And if they end in our waterways, we are going to have eutrophication, which is pretty much the enrichment of water with nutrients. And then we have the algae bloom that we have been seeing happening every year in the last decades. And here is a picture of the western Lake Erie region, as well as the central region, in which we can see how the bloom it's evident from this aerial photograph. So this event specifically happened in 2014, and if some of you might remember, if you are from the area, and if not, I will tell you a little bit about this story. In August 2014.
Angelica?
Yeah.
Sorry, we're not able to see your slides. Just pause 1 second for us, please.
Okay.
Yep, 1 second.
Great introduction, by the way.
Thank you.
So I guess just as Angelica was going to go into the 2014 Toledo water crisis, how many of you who are on the call tonight or were impacted by the Toledo water crisis? Feel free to chat that in the. I'm just interested to see how many me's or yeses I get, because we have 80 participants.
Many yeses, yeah.
Many yeses.
My apologies for not being, I don't know what's going on with the technology, but I do see my slides.
Okay. Yep. Nope. That's. We're getting a lot of yeses on my question. That's interesting. Not good. I won't say good. It's not good, but it's interesting. I see David has a hand raised. Was that a yes? Was that in response to my question, or okay? All right. Thanks, David.
That's what I just did, but it didn't change.
There it is.
Program's gonna give us the dual audio stuff.
Tim said that he can see it now.
Yep, it's up.
Okay.
Go ahead. Yep. Go ahead.
So Angelica,
I will restart.
Yeah.
Not restart, but continue.
we're gonna do over, which is just do the exact same thing you did last time. It was awesome.
I'm wondering, do you guys see this one?
Yes.
And this
yep,
one?
We can see you changing them now.
Okay, but you never saw my slides ever.
We never saw. No.
Okay.
No.
So very briefly, you guys remember my explanation a couple of minutes ago. So this is the diagram that I was trying to show you guys with the different land uses. And I said that high nutrient concentration in the waterways will induce eutrophication and algae bloom. And then I show you guys the western Lake Erie portion and the central portion of the lake that actually, it has a huge biomass of algae bloom in 2014. And then I was saying that in that specific year, in August 2014, more than 500,000 people in Toledo, they were not able to drink water from the lake. And the city passed a do not drink, do not boil advisory. Why not boiling? Because you might think that if I boil the water, maybe the bacteria will die and then it will be okay for me to drink it. Well, the thing is that the algae bloom in the western Lake Erie, they produce a cyanotoxin. So it's a toxin that it's very dangerous for the liver. So if we drink it, it might be detrimental to the human health. So the city was distributing potable water because of the severity of the problem. Okay, so that's a little bit about why it is relevant to understand and to try to mitigate the transport of nutrients into our waterways. Well, now I want to tell you a little bit about history of this area. And I imagine that most of you knows that before we had the Great Black Swamp, but we no longer has this swamp, maybe just a couple of remnants, not even a couple of percentages remains today. And the thing is that almost 200 years ago, the government was subsidizing and supporting the idea of draining the wetland, the swamp. Why? Because here we can see in this diagram a soil profile in which we can see that dark soil. It's very rich in organic matter, and when we drain the soil, now suddenly we have a really fertile soil in which we can plant different crops. In this area, in specific, we have corn, soybean, and wheat. So, but what happened when we are draining the wetland? Now we are switching from one natural landscape to a more anthropogenic or man-made altered landscape. So this image that I'm showing you here, this map, it's showing the western, well, actually the Maumee River, it's here, and it's showing the watershed of the Maumee River. The yellow color represents agricultural land use, and we can see that most of the land is actually farmland. So between 80% of the land to 85% of the land in Ohio, it's from agricultural land use. So that means that a huge amount of both soluble reactive phosphorus, which is another word for saying soluble phosphate, and also particulate phosphate are now moving into the western Lake Erie. So another factor that is affecting is that in order to drain the Black Swamp, back then, a couple of 100 or 200 years ago, they were using a technology that is called tile drainage. And back then, actually, they were doing clay tiles, and they were digging the trenches and putting the tiles in the farm, a couple of inches below the ground, and then this will allow the water in that swamp now to be moved very quickly throughout this new underground tunnel, if we want to think about it that way. Nowadays, it's more easy to install. It's plastic tubes that are perforated, and now the water, it's moving very quickly. So here is an example. And when I learned about this the first time, I actually went into YouTube and I saw a video in which this installation was going on, and you can see that within hours, the water it's moving very quickly out of the land. So what this tile drainage does is it moves the water content in the soil. And here it's a new term. It's called the water table. It's another way of thinking the saturation. So the soil, it's saturated with water. And when this tile drainage is put in place, now that water it's moving out of the system and the water table decreases, or the saturated soil decreases. And this is very beneficial for the plants because now the root system can penetrate deeply and can get access to additional nutrients in the ground. So by draining the swamp, we now have a richer soil in organic matter as well as in nutrients, and the plants tend to be more healthy and also produce higher crop yields. But why this is a problem? Well, the thing is that this map here, we can see here Lake Erie, Michigan Lake, the Lake Michigan, and the colors here are representing how much of the land it's being tiled with the system that I just showed you. So yellow color represents small percentages of the installation of this salt drainage. The darker the blue represent higher percentage of land that has been tiled. And we can observe that the majority of the north part of Ohio, as well as the Maumee watershed, it is bright blue, meaning that a lot of the land in this region has been tiled. So what are the issues or problems that this can have towards our natural systems or our waterways? Well, now we are connecting the land. So when fertilizers are put in the land and we have a rainfall event, now the nutrients that are dissolved in the water will be able to move more quickly, via this tile drainage system and reach the waterways more quickly. What I'm showing here, I'm gonna digest this for you guys. This is a figure showing time in the x-axis, and then discharge in the y, as well as the concentration of phosphorus. And here, the line represents discharge, and then the black dot represents dissolved reactive phosphorus, which is phosphate, and the white open circles represent particulate phosphate attached to sediments, for instance. So every time that there is an increase in discharge, and this discharge is at the tile drainage, every time that there is an increase in discharge, there is also an increase in the concentration of either dissolved reactive phosphorus or particulate phosphorus. So this data is indicated that every time that there is a discharge, these nutrients are also moving with the water out of the system. So what are the implications for this? Well, as I mentioned, we have the blooms in Lake Erie, and there is a very strong correlation in which dissolved reactive phosphorus, the more dissolved reactive phosphorus, the more cyanobacteria biomass. So what this figure is showing here is that phosphorus is a limited nutrient that as soon as the algae has access, the biomass will increase will increase. So this is so far I have explained you guys the relevance and the problem. But as every scientist, we need to look for the solution. And here I am presenting you guys a good amount of solutions that either, federal or state agencies, as well as high education institutions, as well as farmers, we are working together to put these practices in place. And we name these practices best management practices, and for agricultural, then we say agricultural best management practices. And all these practices are put in place to try to mitigate the export of these nutrients into waterways. Some of these practices can target a specific management, if we can think about it like a compartment. So we have the soil management, we have the water management, and we have the nutrient management. And just to mention some examples, for the soil management, we can have cover crop. For the water management, we can have wetlands, riparian, buffers or wetlands at the edge of the farms. And for the nutrient management, we can have precision ag, or we can have different type of filters. And this is the main idea for this for the research that I'm going to be showing you guys today. I'm going to be talking about one specific type of filter that will help reduce the concentration of phosphate entering into the waterways. These BMPs for short, they can also be put in place in the landfill. So we call them infield practices, or at the edge of the field. Once the infield practices, for some reason, couldn't retain the nutrients, and then we want to target them and intercept them at the edge. Just to mention a few examples, here we have infield practices, as I mentioned, cover crops, crops rotation. And here in Ohio, the typical one is corn, soybean, and in some instances wheat. It's also put into the rotation. Then we have edge of field practices, again, that they are put at the end. Here, a couple of examples. We have phosphorus removal structures, which is the one in specific that I'm going to be discussing today. This one will retain only phosphorus. Then we have bioreactors or wood chip bioreactors that they do remove nitrate from the waterways. And then here is just a combination of different ones using wetlands or buffer strips and so on. So that was a little bit of an introduction of, again, why we're here, why we're doing this research. So now I'm going to talk about the specific objective of the research that I'm conducting at Bowling Green State University. So the objectives are the following: determine the efficiency of nutrient removal from agricultural tile drainage using a specific type of filter, iron oxide filter. Also to characterize biogeochemical processes governing the removal of phosphate from the water by this specific filter. And the last one is to determine the role of this organic matter on the sorption of phosphorus onto the media, which is the iron oxide filter. Okay, so I want to show this picture because I think that it's very important to give credit to the farmers. Again, this is a collaboration among many different offices and institutions, and farmers are very important, and we need to recognize that farmers want to be part of the solution. So we all are working together to solve this problem. So now I'm going to show you the filter per se, and I want to make the note that Dr. Chad Penn, which he's going to be in our panel later, so you guys can ask specific questions regarding the design and installation of the filter, but he is the expert. So he actually designed this specific filter, and he was guiding the construction, and even we can see him here. This is with the white cap. He is the expert doing this type of engineering designs. So the filter, in this specific case, the media that he used was an iron oxide. And in some instances, the iron oxide can be put directly into the ground. So when water moves through the media, the nutrients, in a specific phosphate, will be absorbed or sequestered or grabbed by the media. But in this case, he used a septic tank. And the idea is that now the media is confined, and he would like to regenerate the media in situ. What does that mean? Well, the media will have a lifetime. No, only X amount of phosphate will be able to be trapped in the media. And after that, the efficiency of the filter will decrease over time. So the idea is to put some sort of a strong base into the media and remove the phosphate and regenerate the media so that fresh water can move through the filter and keep retaining the phosphate. And the phosphate will be retained in the media and no longer will go into the waterway, at least a percentage. This is how he designed this, to remove a percentage of phosphate from the tile drainage in this case. So we can see here the whole team putting together the system. They have different instrumentation. In this case here, we're seeing an auto sampler. So every hour or whatever is the time frame that they set it, they are collecting water samples, and then later we can analyze the water samples. The day that the installation happened, it was also a day in which many different agencies were invited, and Dr. Chad Penn here in the center, he educated everybody. We did an outreach education in which we learned about this technology, the design, and so on. And he can say more later if you guys have specific questions regarding to this technology. So just let's talk a little bit about the materials that we can use in these filters. the idea is to use a media that will be able to retain phosphorus, something that is very reactive, and phosphorus will feel some sort of attraction and be attached to the media. And there are many different types of one. So steel slag and fly ash, for instance. The one that we use, again, it was a synthetic, if I am remembering correctly, iron oxide. And so this example here is what I was explaining you guys regarding the regeneration. So we can see here the PO4 represents phosphate, and we see the iron and how phosphate is interacting with that iron. So this is how the iron media actually behave. It will be retaining the phosphorus. And then the regeneration will be putting some sort of base, in this case is sodium hydroxide, and then the sodium hydroxide will replace the phosphorus. We collect the phosphorus, and the phosphorus is disposed properly from the site. And then the media is regenerated, and it can be used again. Usually these filters can be designed to have a lifetime of maybe 5 years or so, but with the regeneration in situ, we can expand the time that they can be efficient and in use. So this picture here is showing the final product, and we can see here the septic tank. We can recognize that as a septic tank, and the media is inside the septic tank. Here we have the inlet, so water will move through this one. It will be distributed inside the media, and then it will go into the outlet. And here I'm showing you guys the outlet that it will go into the waterways. So as I mentioned, the system has an auto-sampler, but because I was interested in collecting dissolved organic matter decompose quickly at high temperatures, and what I decided to do is go to the field and actually grab samples, and the very same day I filtered them, and within a week I analyzed my samples with respect to organic matter, because I wanted to actually have a real snapshot of the type of organic matter and concentration at the specific moment that I was collecting. So this was a family activity. Actually, my whole family, for a couple of Sundays, we went to the farm and we collected the water. So here you see myself and my family collecting the water at the inlet and then at the outlet. And I'm going to show you how the water looked like before and after moving to the filter. So this sample here, it's in the inlet, and then this sample here is at the outlet. And we can see after I filter, I filter using a paper filter, we can see how much organic matter and debris or particles are in that filter versus this one. It looks relatively clean. And we can also see the unfiltered, the filtered inlet solution and the filtered outlet solution. So we can see that there is a difference in colors. And that difference, whatever was in that solution, now it's attached into the media. So we can, just by looking at the color, we can see that the filter, the phosphorus filter, is retaining whatever constituents are in the water. So I'm going to show you only two graphs of my data, because I want to show you guys how efficient this filter is. We see here in the x-axis time, so this were the different Sundays that I went there with my family, and this is the phosphate concentration in milligrams per liter. And I'm also showing you guys two lines. Here the black line is the inlet concentration, so what it's coming from the land, and the red one is the outlet concentration, what it's coming out of the filter. And we can see that here is the concentration of P. There are differences in the concentration, but when we look at the outlet, in most of these days, I got 0 concentration of phosphorus. So the filter is extremely efficient removing phosphorus from the system, at least during that time that I was collecting data, and this was pretty much at the beginning of the life of that filter. But I also observed that not only phosphorus was being absorbed by the media, also dissolved organic matter or total organic carbon that is here in the y-axis, and again I have time. And it's the very same legend, inlet and outlet. So the concentration of organic carbon was high and then it was low. And this data, it's telling me that not only phosphorus is being retained by the media, also organic matter. And this gave me an idea because later I'm going to engage in a conversation with Dr. Chapin because I think that this data will help inform him better on the design of the filters. Because my hypothesis is that potentially the organic carbon is competing with the phosphorus, and the active sites that will trap, retain those phosphorus might be occupied by the organic matter. And that's what's going to be the work of my master's student, which is also, she's going to be part of the panel. So if you have questions regarding the experiments, she will be able to answer. Again, this is the first, she's from Bangladesh. Bangladesh, and she just moved here, so she's still getting acquainted to the research, but she will be able to answer some basic questions. So what is she going to be doing? Well, she's going to be doing laboratory experiments in which she's going to have a different set of parameters, and we want to see if, in fact, organic matter is competing with phosphorus. So she's going to be doing what is called column experiments or flow-through experiments. So we're going to have a influence solution, which is going to be mimicking like the solution in the land or in the tile drainage. That solution will move through the tiny columns which are mimicking the filter media, and then we're going to be collecting that with the fraction collector. And here is my student Fatima, that you guys are going to be meeting her briefly. So here is a little bit more details. I'm sorry, maybe this is too much details, but I will just very briefly discuss some of them. These are the specific experiments that she's going to be doing in the lab in the next months. And most of the data that she's going to be using was informed from the field data. For instance, the pH, we're going to be mimicking the pH of the concentration of the influent solution in the tile drainage in the field, as well as the organic carbon concentration and phosphorus concentration. And then we're going to be doing a series of experiments in which it's going to be just irrigating the columns with phosphorus, or first organic matter, then phosphorus, and then competing, both of them together. And we're going to be doing this at two different flows, high flow and low flow, because we want to mimic when we have low precipitation events as well as high precipitation events. And this is something that I need to discuss further with Dr. Chapin, because we need to be informed from what's going on in the field to be representative to the column experiments. And my student, she's going to be measuring a lot of different parameters, pH, organic carbon, phosphorus, and we're going to be characterizing organic matter as well. So I do want to end this presentation with a positive message, and it is that we all want Lake Erie to be a clean lake. And we can think about a couple of years in the 1980s that Lake Erie was clean, but now we are maybe in this situation, and if we want to move forward, we need to still do farming, but also incorporate BMPs, and then hopefully we're going to have, again, our Lake Erie clean and we can enjoy the water. And with that, I want to say thank you, and I'm ready to take any questions.
Wonderful, Angelica. Thank you. So I am Kevin McClooney. I am an associate professor in the biology department and part of the Water Center. And I am going to lead the sort of question answer discussion, really, we want a discussion portion of tonight. And so a couple of things. First of all, if you see a button that says participants, if you press that, at the bottom of the participants window, there should be a spot for you to raise your hand, your digital hand. So if you would like to ask any of our panelists a question, you can raise your digital hand, yep, just like David did. or you can put your questions directly in the chat box and I will read them. Right now, I'm going to turn it over to Dr. Vazquez-Ortega, who will introduce the panelists.
Okay, thank you. So I have been mentioning Dr. Penn a lot in this presentation, and he is here part of the panel, which I'm very happy and thankful for him to decide to participate in this event. And I want to introduce him. So Dr. Penn is a soil chemist at the USDA Agricultural Research Service in West Lafayette, as well as an adjunct professor at the Department of Agronomy at Purdue University. He joined the USDA in 2016, and he was a professor of soil and environmental chemistry at Oklahoma State University. And his current research focuses on nutrient transport mechanisms, improving plant nutrient recommendations, thermodynamics of surface reactions, design and construction of phosphorus removal structures, and animal waste management. Okay, and should I also, I'm sorry.
I can introduce, should I go ahead and introduce our student panel? Well, she's not a student anymore, but our other panel member?
Mm-hmm. Yeah.
Okay, so another person who was pretty critical in this particular project, in this research arena, is Dr. Issa Scott. And Dr. Scott currently, she's a postdoctoral researcher at the University of Maryland in conjunction with USD ARS in Beltsville, but she just recently graduated from Purdue. She's my first PhD student from Purdue, at least, and I really like to brag about her. But anyway, she got her degree in December in ag and biological engineering, and her work was critical to the design of the structure because she was specifically working on this media. It's the iron coated activated alumina, and she was also did some really nice experiments on the regeneration technique, which went became important in how we actually designed it so we could regenerate it later on in about 10 years probably in situ. And she's also done some really nice work during her program on looking at the impact of excessive saturated conditions or reducing conditions on phosphorus removal structures that are constructed with iron oxide media, such as what is shown in the unit that you're looking at tonight.
Awesome. So can I also introduce Fatima, my master's student? I'm sorry, I don't know if Isis wanted to say something.
Yeah. Go ahead.
So can we bring Ume? Okay, awesome. So Fatima, she joined BGSU last fall, and she was taking classes abroad because of the COVID-19, but this semester I'm so happy that she was able to join BGSU. And now she's going to be working in the column experiments as I just mentioned. So please address any questions that you guys have to this panel, and we're going to be doing our best to answer them.
Yeah, so if you have any questions to ask that you'd like to ask via video, you can raise your virtual hand. And if you want to type them into the Zoom chat box, I will read them. I'm going to get us started with one. And this is for each of the panelists in turn. How did you become interested in water quality in the first place?
Okay, I think that I can go first and then chat if you want to go. Water quality. So I think that when I came here, when I got this job, it was very impacting to me to see the algae bloom. Many of the high-ends, many of my students, they have never been at the lake when these algae blooms are happening. And that was one of the first things that I did when I came here. I actually wanted to see the lake, the bloom, and it was kind of like sad at the same time that we cannot enjoy that water, that body of water. And that and the current environment in which we need to write proposals and get funding, that was the topic. So, and it was of my interest because I want to contribute to the problem. I want to contribute to the solution. I'm sorry. Yeah.
Great. Chad?
As a soil chemist, I just look for opportunities to solve problems. So I'm working both in the agronomic realm with trying to increase crop production sustainably, and in addition to reducing environmental impacts and solving environmental issues, water quality issues. So I'm, anywhere I can use soil chemistry to do that is I consider an opportunity and a challenge. So I've been involved in working nutrients in some shape or form, for over 20 years now, and that's probably not going to change.
So for me, I got involved with water quality during my undergrad studies. So I've always been interested in sustainability. And I do believe that one way that agriculture can reach that stage is through water and soil conservation. So that's my goal as a scientist.
Wonderful. May?
Okay, so as Isa said, I also got involved with water quality in my undergrad, and I just graduated. So from the place where I belong in Bangladesh, I have seen a lot of pollution here, and the underground water gets polluted with a lot of pollutant. But here in BG, I have been introduced to algal bloom. So I'm learning, and I'm looking forward to working more on water quality and sustainability. Yes, that's my goal.
Thank you. So I think we'll do a question from the chat box, and then we'll go to Ed, who has his hand raised. The first question here is from March. What is being done to decrease the amount of phosphorus being applied to the land?
Okay. I think that this is something that Chad and I, we both can say something. There are many, as I mentioned at the beginning, many best management practices that can be put in place in the farm, in the field per se. One of them that I always find very fascinating is one named precision agriculture, in which farmers, let's say that you have, this is the map of your land. So farmers will take soil samples across their land, and they will actually know how many phosphorus is the soil containing across their land. And Precision Ag, it's working with that, with an actual map of your site, and then they have expensive equipment that will allow them to actually put in the land or in that specific area the exact amount of fertilizers that it's needed in order to achieve the agronomical value. For corn, for instance, farmers are looking for an agronomical value of 40 ppms, which is milligrams per kilograms of phosphorus or bioavailable phosphorus. So when they do this type of distribution, they are only targeting the specific range that specific land is using. And that's more sophisticated, but doing the first portion of sampling your field, which is known as soil testing, to know how much phosphorus you have in your land. That's one of the BMPs that it's mostly used by farmers. And then the farmer has a good idea of not just putting the nutrient, but also putting it if it's needed in the land. So Chad, you want to say something else?
Yeah, I mean that's basically it. It's soil testing, nutrient management. You keep tabs on how much is in your soil, and you know how much the crop is going to require. So you only apply the amount necessary for the crop for the crop yield to be maximized, and don't add any more to that. So and like I said, it requires soil testing and knowing what you have, and then following your nutrient management guideline so that you don't add too much.
And also we can also say about the cultivars that nowadays are more efficient in absorbing phosphorus from soils than before, right? So genetic breeding, we can also thank genetic breeding for that.
Yeah, a lot of your modern varieties will take up a tremendous amount of phosphorus out of the soil. That's a good point, Dr. Scott.
Wonderful. So next we're going to have a question from Ed. I'm asking you to unmute, and you can go ahead and, when you're unmuted, there you go. Yep.
All right. Yeah. Thank you, Kevin. So I had some general questions in the chat that I popped in when I saw the 0.5 ppm influent, which seemed a little on the high side. And then I got the answers back that you kind of forced it by over fertilizing and what have you. So that's a concern because the absorptive capacity is greatly influenced by the influent concentration. So whatever bench work you do to simulate field conditions should be, you could do the 0.5 to get your good results and look at the regeneration factors. But if if the base load is closer to 0.1 or less, you're going to see a lot different results on the absorption capacity and then obviously your exhaust stream.
Yes, yeah, that's true. And we do not have 0.5 milligrams per liter dissolved P flowing into that thing. I wish we did because it would make a better demonstration. We don't. When we get the big flow events, like Angelica showed that, with your big storm events, you tend to get your highest concentrations. And so occasionally we'll get, for the big events, which you got to remember that delivers, 1 or 2 events per year is what delivers around 90% of your dissolved phosphorus load. So for the big events for that field, you get about a flow weighted average dissolved P around 0.2 milligrams per liter. The rest of the time, the concentrations are much lower than that. And so so that's why when Dr. Scott was doing her research on this, she was using, okay, did you use 0.2 milligrams per liter, 0.5? I use 0.2 now for everything, but at any rate, we use low concentrations, and for this field, quite frankly, we'd like to get the soils built up a little bit higher so that we have a better demonstration.
Yeah.
Yeah, I guess.
Oh, go ahead.
Yeah, go ahead.
So I was just going to add that that's something that is very important for us to find hotspots in the fields. So we know that there are places that you will have higher sources of phosphorus, right? And that's why, for example, we like to install these phosphorus removal structures where we know that we will have a higher phosphorus concentration coming in, because you are 100% correct. The absorption is concentration driven, right? So the higher concentration for most of these phosphorus sorption materials, we will have a more absorption. And just double down on what Dr. Penn said, that the big events, which happen once or twice a year, deliver most of the phosphorus from the field. And that's why we are interested in those big events.
But even that is a double whammy. Sorry, Kevin, just one more comment, and then I'll let someone else speak. So then you've got the other factor defeating you if you're relying on the big events, and that's contact time. So now you've lost, because of the high volumes, now you've lost your contact time. So you can't possibly treat all of that phosphorus by absorption anyhow without bypassing 90% of the flow.
No, that's not true for our systems. At least the way I design them, we design them to meet a minimum retention time at the maximum flow rate. So we characterize the site and determine, what are going to be the peak flow rates, what's going to be high, and then we try to design that structure if feasibly possible, and a lot of times we can, to be able to handle 100% of that flow rate, or maybe a little bit more. And while achieving that flow rate, also achieve a certain retention time. Now, that gets to be a really big challenge for some sites and for some media. One of the nice things about this media, one of the reasons why we chose this media, again, it's an iron oxide, it's an activated alumina coated with iron oxide. It only requires retention time of seconds. So ESIS did all of her flow through work on this using a 17-second retention time. And so if you only need to achieve a 17-second retention time, you can achieve a very, very high flow rate. That's one of the reasons why we chose that material. Now, for other materials, you need a longer retention time. You need 10 minutes. And again, if you're trying to design your structure, which I do, to meet that minimum retention time at the highest flow rates, that often translates to a very large structure. I'll give you an example. One of the materials that I really like to use a lot is metal shavings. It's a steel metal shavings, and mix it with gravel. And those metal shavings start to rust. They form iron oxide. It makes a nice piece of material, but you need usually need a good 10-minute retention time. And so if you want to handle, let's say, 300 gallons per minute or 500 gallons per minute or something high like that, and still achieve a 10-minute retention time, it requires a very, very large pore volume. So if you want to meet both of those, because if you think about that, retention time and flow rate are kind of inversely proportional to each other. If you want to meet both of those, you have to build a structure with a very large pore volume, and a large pore volume means lots of media. So this sort of thing we've built into our, we have a design software that's it's free, it's open to the public. It's called P-Trap, and it takes that into account. So you choose your retention time and the flow rate you want to meet, and it will design, if possible, a structure for you that will meet both of those constraints. And if it's impossible, it will give you suggestions to tell you you need to make your structure larger so that you can meet both constraints. So that's a good point. It is critical. You have to meet both retention time, and you want to be able to do it at the high flow concentrations, high flow rates, which can be very tough for some media. But that's one of the advantages of having a material that can absorb phosphorus very, very, very quickly in a matter of seconds.
And that's one of the advantages of the Phosphorus trap software as well, the P-Trap software that you can use. It's online, available for everyone. That you can design your structure based on your specific needs, and based on your incoming concentrations, on your higher flow rate. It's the phosphorus removal structure is very adaptable to each situation.
And for any media, whatever media that you have, if it's been characterized for P sorption, I mean, people send me media all the time. I've got media from around the world, and I characterize it, and I put what we call the phosphorus removal design curve. I put it into the library, and then it's available to anyone who's using that software online, and you can pick that media and design your structure with a certain type of media theoretically, and then try different media in it and see what it would look like as well.
That's very interesting. I want to get to a few more questions in the chat, and you're always welcome to stick around for conversations afterwards as well. So the next question, a little different. Are there any opportunities for BGSU students to get involved with research with the nutrient management and the Great Lakes? And I'll send this to you, Dr. Vasquez-Ortega.
Can you repeat the beginning? For some reason, you stopped.
Yeah. Are there any opportunities for BGSU students to get involved in the research you're doing on nutrient management in the Great Lakes?
Yeah, there are many, and I am very happy to say that my lab thrives with undergraduate students. Every summer, I encourage undergraduate students to work in my lab. Bowling Green State University has an opportunity in which undergraduate students can apply for small scholarships. So if you guys are interested, you can search Center for Undergraduate Research Scholarships, and you guys can have, you need to write a very short 3-page proposal, and then if you qualify, you will be able to to get the scholarship and participate, doing research in my lab. Also, if I do put grants and I have money to pay undergraduate students, I can also hire undergraduate students. And I have had, I have been here at BGSU for maybe almost 4 years, and I think that I have been working with more than 8 students. And I think that some of them are already, part of the participants, that they have had the opportunity to work in my lab and work in the different projects, and this is one of them. Actually, for this summer, I'm going to have undergraduate student working with Ume, helping her in this research. Hopefully, if she gets the course for short scholarship. But yeah, there are opportunities. So if you want, I think that at the end of my presentation, it's my email. You can email me, and if it cannot happen this summer, maybe another summer, or during the semester as well.
Yeah.
Hey,
I was going to just ask one last question, and then we're going to officially end, but then unofficially continue discussing. So you can stick around and continue discussing, but I'll have one last official question. Do you suggest these might work for CAFOs?
That's a very good question, Chad. Do you? Because I know that you have
combined animal feeding operations.
I know that Chad has published papers regarding using this in poultry areas, but you can say something more about the confined facilities.
Yes, you're right. You can use these anywhere you have high soil test P. Okay, so that can be urban areas. We've built them on golf courses. Anywhere you have soils built up high in phosphorus, doesn't matter what the land use is from. It doesn't matter if it's from applying too much compost, manure, chemical fertilizer. If you have high soil test P, then you potentially have high dissolved P losses in runoff. And once it's in flow, or tile drainage, but once it's in flow, if you can capture it, you can filter it. So yeah, and we've built them in several states on CAFOs. We've got one on a CAFO in Western Ohio. Yeah, absolutely. In fact, they're one of the main targets because CAFOs tend to have their farms tend to have higher soil test P concentrations than your grain farms, right? Because CAFOs, if you look at historically the nutrient cycling or lack thereof that occurs there's a bit of a geographic imbalance in that those CAFOs are accumulating phosphorus from the grain that's being imported to the farm to feed the animals, and then the phosphorus contained in that grain, it's not leaving with the animal, not very much anyway. Most of it's going through the animal, coming out in the manure, and the manure stays on the farm. So you imagine you're importing all this grain and the phosphorus with it from various places in the Midwest usually, and then you feed it to your animals. It stays on the farm in the manure. You keep applying it to your soils, and it starts to accumulate in the soil. So CAFOs are in a situation where just because of that nutrient cycling or lack thereof, they tend to accumulate phosphorus. Whereas grain farmers, they're paying for their fertilizer. They're generally, for the most part, not going to over fertilize because that hurts them in the pocketbook. Whereas for the CAFOs, it tends to be a little bit more of an issue of waste disposal, which it's unfortunate to call it that because it is a resource. The manure is a resource when it's used properly, right? But sometimes it turns into that.
Great. Yeah, I think that's an interesting way to think about it. Well, Tim, did you want to wrap up or you want me to do that?
I just wanted to, I'll let you do the official wrap up, Kevin. I just wanted to, I wanted to sneak in one question,
okay.
just at the end here. The question really was, so when we think about the economics, right? So farming economics, how would you address a farmer that says, well, we live on, razor thin margins? How would the installment of these P traps, either, what's the upfront cost versus the return on for a farmer? How would we convince them that these would be cost efficient upfront and also save them money in the long run while, at the same time, being beneficial to the lake, right? So how do we meet all those three?
Well, I think that I have an idea, but Chad, you actually knows better how much they are. I have heard that maybe between $10,000 might be the cost of one of these filters, but I imagine
Depends on the size. If you're building one for a great big, if you're building one for a great big county drain that's draining hundreds of acres, it's gonna cost more. But for a lot of the small for the for your like 20-acre fields, a lot of times it can be $10,000, less than $10,000 in a lot of cases. But when you get to it, when it comes down to it, is that it's not making any money for the farmer. All right. It's not increasing their yield. So they really don't have any, they don't have economic stake in it. And you could say, oh, well, we could take this phosphorus that we trap in it and extract it, with our regeneration procedure. You got some phosphorus that you pull back out of it and say, oh, they got this phosphorus fertilizer they can use now, but it's hardly anything. Okay. The amount, the issue is it's a paradox of phosphorus requirements. We don't need very much phosphorus to make a pond or a lake, aquatic system to go eutrophic, but we need a lot of phosphorus to grow a crop. And there's very little relative to what's applied to the field. There's very little phosphorus that's leaving. If I take, from a filter, all the phosphorus that we capture, so let's say after 10 years, I don't know what we have, and actually I can pull up the numbers right here. In 10 years, theoretically, we could be around like 20 pounds of phosphorus, 20 to 30 pounds of phosphorus. Big deal. 20 to 30 pounds of phosphorus, that's not enough to fertilize even 1 acre. All right. So that's like $30. That's probably only $15 worth of phosphorus on the market. All right. $15 worth of phosphorus is nothing economically to a farmer. But that 20, 30 pounds of phosphorus, if that reaches a water body, that is very devastating to eutrophication. That little bit of phosphorus is inconsequential to the farmer, but it means everything to an aquatic ecosystem. That's why I call that the paradox of phosphorus, and that's really the problem that we have. So the farmers don't really have much economic stake in this.
And if you multiply that small amount by all the fields within the Western Lake Erie, within the Maumee River watershed, then we have a huge impact in the lake. But for the farmer per se, the amount is insignificant.
And as far as, so part of the question was about cost of who would pay for it. And so I think you are deduced by now that the farmer's not going to pay for it. You get a few once in a while. You get some adventurous farmers and some guys, they really, they really they like trying new stuff and they want to do the right thing. But usually 9 times out of 10, it's paid for by nonprofits. So, TNC has paid for some of these things, but for the most part, it'll be paid for, and it's cost shared by the NRCS, the Natural Resource Conservation Service. They cost share it in their, it's called the EQIP program, Environmental Quality Incentives program. And so they will pay for it in certain states, just like they pay for nitrogen bioreactors. They'll pay for riparian buffers, stream fencing to keep cattle out of fencing. So in other words, tax dollars is what is used to pay for a lot of conservation practices, including this one.
No, that's great. Thank you so much. I think that's a great way to kind of wrap this up. I mean, the technology is really fascinating. The work that you guys are doing is really important. And I just wanted to say, as co-host, just thank you so much and for being here. We really appreciate the time and the effort you put into Angelica making the presentation, giving the presentation, and for the panelists to answering all the questions. Kevin, did you want to officially end us? And thanks everyone for coming.
Thanks everyone.
Yeah, that was great, Tim. I mean, I think he put it well. We want to thank all the panelists, and we're going to be doing the unofficial. I just want to be clear, unofficial, the official end, but we're going to unofficially continue for probably another 15 minutes or so, and I'll try to get to some of these questions in the chat that we weren't able to hit yet. But I just want to thank all the panelists and everybody that was involved in helping set this up. Be aware that there will be an evaluation survey, survey for the event that you should get sent via email, and your feedback is really helpful as we work on continuing these. And this is our third event, right? So we've got events planned out now all the way into the summer. So be on the lookout for more dates and more speakers. With that, I'll just say thanks to everyone. And if you want to stick around, I will keep going through the questions. Okay.
Sorry, I just have a short question.
Go for it.
The media, how long will you replace the media every? How long will you change the media? I mean, it's kind of filter, right? For me, how long will you change it? For the
this one was designed. So one of the things that goes into a design is knowing the P concentration going into it. On average, it varies throughout the year, and with the flow events, as Angelica showed, and the annual flow volume. So your volume times the concentration is your mass of phosphorus. So knowing that and knowing how much you want to remove and how long you want it to last, those are things you get to choose as a designer. So we purposely designed this, assuming this thing. We assume that the inflow concentration, we had some measurements, that it was 0.2 milligrams per liter of dissolved P going in. We had estimates of the annual flow volume. And based on that, knowing that we wanted to remove 40% of the cumulative load, that is all the mass of phosphorus that flows into that unit over 10 years, however many pounds that is over 10 years, we wanted to remove 40% of all that. So that's kind of it's a design, it's something you choose as a designer. We could have designed it to remove, 60% over 3 years, or, I don't know, 40% over 20 years, or whatever you want. That's up to the designer. Okay. This one was for 10 years, 40%.
Okay, so does that mean if it achieve the goal, so you will replace it? So how to deal with the designing filter? Is that disposal, or you can redesign? It's iron and sulfate, right? It's the main chemical is iron and sulfate structure, right?
It's not sulfate. It's an iron oxide.
Okay.
And it's an iron oxide it's an iron oxide coating onto an aluminum oxide, an activated alumina. And so like what Angelica was saying, and also ESIS, this is what a lot of ESIS's research was on. ESIS developed a technique for regenerating it, so that instead of cleaning it out, some materials, other media are less expensive, and we'll just clean it out and land apply it somewhere safely, and then put new media in. But for this stuff, we can regenerate it. And ESIS, like I said, she I don't know if you want to say anything about your regeneration techniques.
No, yeah, I can talk about that. So the idea is that with these materials that are rich in iron and aluminum, we can have this type of regeneration, because the same way that we can force the particles, breakout particles as well, right? Oh, sorry.
Yeah,
can you hear me now?
Yeah, we can hear you now.
Okay. But yeah, the idea is just that you can treat the media once it is saturated with phosphorus, and we treat that with a strong base. So the media will prefer to bind with that strong base instead of phosphorus. So it releases the phosphorus that is within its surface, and then it grabs the OH back. and then it's regenerated, and it can start again with all the process of removing phosphorus from the flows. That phosphorus that is released is then we can then get that back to a tank or something like that. But as Dr. Penn said, it's a low quantity for agronomical purposes, but it's a high quantity for environmental purposes.
Thank you so much.
Yeah, of course.
Thank you. So the next one should probably be a very short answer, but can you give a sense of how many acres of land each filter can handle?
Yeah, I wish that was a short. I'll give us the shortest I can.
The design itself is that short.
Yeah, that's the problem. Is they're custom designed for each site. You know, so I've designed them for 100 acres, and this particular one that you saw tonight is for I don't care if it's a 20 or 30 acre field. So you can design them for anything. It just depends on if you got the money to build it.
I think that's a great short answer. The next question is sort of asking you to make some predictions, I suppose. Will eutrophication spread to the other Great Lakes if this problem isn't addressed? I live outside of Chicago, and I'm wondering if, even though Lake Michigan is deeper and colder than Erie, eutrophication and harmful algal blooms could be a problem there in the future.
Well, I think that we do see this eutrophication and algae blooms in Lake Erie, because Lake Erie is one of the shallowest and warmer lakes of the region. So this is why this lake is so active or alive, if you want to think about it that way. It will all depend the export of these specific nutrients, and again, phosphorus has been linked to the biomass, to the growth of the algae. Nitrogen or nitrate, it's going to be more related to the toxicity. Most of the cyanobacteria produce cyanotoxins. It will all depend on, again, weather conditions, as well as how the land use in that area, how much agricultural and how much or little best management practices are being put in place. I don't know, Shad, if you want to say something else.
I'm a soil scientist.
Yeah, maybe Dr. Kevin.
So, Chad, can I
Dr. Davies can say something. Yeah.
Yeah, I was just gonna say I'm not part of the panel, and I do my best to keep my mouth shut on most of these. But this one, I think I can at least help with this question. We do see harmful algal blooms in all 5 of the Great Lakes. So in Lake Michigan, will the main body of Lake Michigan ever experience harmful algal blooms like we see in the Western Basin of Lake Erie? Probably not. But in Green Bay, the Fox River that flows from that kind of connects Lake Winnebago to Green Bay, that's a nutrient source, so Green Bay experiences these types of blooms. Saginaw Bay in Lake Huron, you have Bay of Quinte and other areas along the New York coastline of Lake Ontario, and even the western portion of Lake Superior near Duluth, Minnesota has also, and the Apostle Islands has seen several harmful algal blooms and eutrophication issues in the past 5 to 7 years. So all 5 of the Great Lakes are impacted by cultural eutrophication. And Western Lake Erie is really just our kind of poster child for this, type of problem, but it is a region and, quite frankly, a global problem. So,
just adding on that, there is a piece of research by Dr. Sinia. I think she's from Stanford University, and they modeled what will happen to different water bodies around the world in the 21st century, given the situation that we have nowadays, and given all the scenarios with climate change and the rising temperatures and more frequent and more intense rainfalls. It's a model, right? It's a representation of reality based on what we know nowadays. But according to their research, eutrophication will increase and will get more frequent as we go deeper into the 21st century.
Isis, since we're on the subject of climate change, that leads into one of the next questions, and maybe you want to give it a shot. And so we have a question sort of asking about the filter structures. Are they going to be able to handle more extreme rainfall events with respect to climate change?
I think that's
Well, yeah.
depends on the design again, no?
Exactly, yeah. That's the advantage of these phosphorus removal structures. They can be as adaptable as you want. But again, as Dr. Pan said before, they are designed based on the maximum flow that are expected, for example, for a 10-year storm. But you can design it for a 100-year storm, for example. It will be more expensive, you need more media, but you can design according to your needs. If one of your needs is, okay, I want to be able to treat for the effects of future rain, more extreme and more frequent rainfalls, then you can do that. But yeah, it will depend on the objectives and possibilities of the place where you are going to install it.
Yeah, and I think it's more also cost effective, you know, whatever, yeah, how much they're willing to pay and these events, yeah.
Yeah.
And Alga, we've got a question that probably would be good for you. So there's a question, I'm going to kind of try to summarize it, but basically talking about how the soils in our region have lower carbon content than they used to, right? That we've lost a lot of sort of native higher soil carbon soils. And what is the effect of that? You know, would we be in a different situation if we still had those?
I think that that's true because, you know, this was the former black swamp, so organic matter was very rich in the region, and most of the soils are known molly soils, which contains a very high, thick organic horizon. One of the practices that actually is depleting carbon concentration in our soils is by doing tilling or plowing the soil. When this type of practices is done by farmers because they want to prepare their land to plant their crops, they disturb the soil. And during this process, organic matter, it's more likely to be decomposed by bacteria, and then CO2 is emitted into the atmosphere. And this is also contributing negatively to the climate change. And I think that, you know, we also need to start changing our vision towards, instead of these soils being a source of CO2, actually being a sink of CO2, you know, accumulating organic matter into, you know, making that organic matter being part of the soil. And I think this is now, maybe with the new administration that we have in the in the US, and be more towards recognizing climate change. Maybe now we're going to be doing more and more projects on thinking that let's have our soils as sinks instead of being sources of CO2.
Great. I'm going through a few more here. I saw one about grass waterways, which seems to have been addressed somewhat in the chat, although I could maybe add to that a little bit myself. I've done a little bit of work in that area.
Yeah, you are the expert there. I am not.
Well, Chad, you know, I think Chad makes a good point, but I think that there's still some questions about how much it can remove dissolved phosphorus as well.
Yeah, it's mainly more particulate phosphate.
Right.
Phosphorus, I'm sorry.
Hey, Kevin, this is Ed Weinberg. Pardon the interruption, but you know, I just had some minor eye surgery this afternoon, so I'm basically squinting now. So I gotta bow out. But I did want to interrupt. Based on the grassed waterways, I put in the chat a proposition to BGSU researchers and students to collaborate with me, ESRI Consulting, on a concept of stacking these adsorptive media with other BMPs like grass waterways, which makes a world of sense because you remove the sediment, use the grass filter as a sediment trap to allow free, relatively free solids to hit the media. But another natural stacking would be post a wood chip bioreactor. And now you get nitrate and phosphate all in the same best management practice. So I'd like to propose something like that to AFRI Foundational and Applied Science program. So if anyone from BGSU is interested in taking the lead as an integrated project to AFRI Foundational, I think Angelica has my email address. So
Okay.
on that note, I'd like to bow out. But thanks for letting me interrupt.
And
Thanks, Ed.
actually,
I think we're nearing the end here, but I think that's a good point. I'll let others weigh in, but I think that it's there's lots of potential solutions, and we can think about ways of combining them to produce solutions.
yeah, and I want to say, and Shad, maybe it's more familiarized with the project if it's going on in this way, but my understanding is that initially that was the idea for this specific field, that we're going to have a wood chip bioreactor intercepting first the water for the tile drainage, and then we have the P filter, because again the P filter will only solve the problem of phosphorus, and then the wood chip bioreactor will solve the problem of the nitrogen. But I don't know if the installation happened. Do you know, Chad?
No, it never happened, and like you said, it was supposed to happen. It didn't, but we did end up doing that at another site in Delaware County, just north of Columbus. We did that. We have a treatment train of a bioreactor in line with the P removal structure. The only thing about that is, keep in mind that those bioreactors are designed to have a super long retention time, many hours. So as a result, they can only handle a very low flow rate, which makes it easy. If you're plumbing that into a P removal structure, it's a piece of cake, because I'm used to designing them for peak flow rate. And so there's a little bit, you can do it, and we've done it, but you have to design them so that the overflow is most of the water that flows in the bioreactor is not going to be able to go through it. They just can't handle much flow rate. So you have to build, we built a bypass on it to take any excess water from the bioreactor and put that into the P removal structure. So the P removal structure is fed by water that's been treated by the bioreactor and the bypass water from the bioreactor. That's the only thing I keep in mind on those, is nitrogen and phosphorus and the timing of those things, they're very different.
But I just mentioned that one as one of many, because you can do the same thing with an enhanced wetlands, and just egress it with a water control structure loaded with the media.
Yeah, wetlands. Are people interested in using P sorption materials in wetlands? A lot of people in Europe have done that. Some people in Florida. Yeah, you're right. It's a good point.
You could even do it with sedimentation or infiltration basins.
You can convert, Ed, you're right. You can convert a lot of things into P removal structures.
That's what I'm thinking. So I think it would make a good proposal to AFRI Foundational, but I'll leave it at that, and thankfully bow out tonight.
Thanks,
a great presentation.
Thank you for joining.
Thanks, Ed, and thanks everyone for coming. I think we're going to go ahead and end it here, but really appreciate everybody for joining us, all the panelists, and we hope to see you at their next one, which will be in approximately 1 month. Look out for emails and advertisements about that.
Thank you. Bye-bye.
Thanks, Kevin.
Take care, everyone.
Thanks. Good night, everyone.
Angelica, take care.
Yep.
Good night.
Well done, Angelica. Great job.
Bye-bye.